My name is Andrey Breslav. I work for JetBrains on Kotlin. And today I'll try to communicate some of the experience on flexible types that we've had recently. So Kotlin, two things you need to know today. Kotlin is a statically typed language, and it's Java interoperable. So these are two things that kind of impose all the difficulties I'll be presenting today. So alternative title for this talk is how we learn to stop worrying and give up soundness. Actually, we gave up two kinds of soundness at once, and I'll try to elaborate on that a little later. So this ability to give up something as precious as soundness has a lot to do with the question, is this glass full? And I, as many of you in this room, am a kind of person who has the luxury to being able to say that it's full enough, because we mostly stuck to what works. Or we can say that it's practically full. So sometimes we can afford to give up a theoretically nice property. So one of the ideas behind Kotlin when it was initially designed was to make it safer than Java. You can get much safer at runtime, of course, but you can try to prevent some of the common errors at compile time. And here are 4 points of what we kind of thought we prevented. These are nullable types that fight against null pointer exceptions. These are read-only collections, where you can express in Kotlin whether your collection is supposed to be modified through this reference or not. So you can express that this list is not supposed to be modified, or that this method is not modifying the argument collection that it's getting. Also, there is a holy grail of fixing the covariant arrays that are in Java since the beginning. And we thought we fixed that. And of course, Java has raw types, and we have no raw types. So that last point here should be no raw types. So these were the 4 ideas we had. And now we have Interop. So we have this somewhat nicer language. And we have these constraints. We want to be interoperable with Java. Actually, it's both ways, but I'm now only talking about Kotlin calling Java, because the other way around, it's all easier. So when Kotlin calls Java, there should be no overhead, neither runtime nor in the code. So the call shouldn't be bigger, longer in the code, and shouldn't take any extra time. We kind of manage that. And also, we are not supposed to prevent the intended use of the API, because sometimes the API was designed, for example, to take an array of objects, which most likely means that this method is working on any kind of array. And if it's not malicious, it's not putting anything wrong into the arrays. It's probably only reading them. Like this one is supposed to count how many non-null elements are there in the array. And if in Kotlin we say that for us, an object array is invariant, it means that you cannot put an array of string into this method, and this prevents the intended use. So this is something we cannot afford. So we cannot make this code read, because otherwise it would be not enabling the use of the library. And the last point here in the interop is that the interop shouldn't spoil the pure Kotlin situation, if possible. So if you're not interoperating with Java, you're as safe as Kotlin can possibly be. Any questions at this point? It should be pretty straightforward. So actually, something should seem fishy already from the previous slide. And the whole point of this talk is that those two things are contradictory. So you can't get both smooth interop and type safety at the same time. So let's start with nulls. These are like another holy grail of very many attempts by many people. So what do we have in Kotlin? So you know the Java situation, right? Yeah, I have a string. I can put a null into it, and then blow up at runtime by trying to dereference it. And Kotlin, if I say a string, it's a string. It's not a null. So you're not allowed to assign a null there. You don't blow up. And if you want a null, and somewhere it's not a string, it's a string question mark, which is a nullable type. And that you cannot dereference without some extra ceremony around it. So we transferred the error from the runtime to compile time. And there are some special devices in the language, quickly going over them. So first thing, you can check for null, and then it's OK. You can even check and return, and it's OK. And then there are some special characters you can type in, either check and not run if the receiver is nullable, or blow up if the receiver is nullable, or even have this short form of if that groovy people named an Elvis operator. Anyway, there are some nice devices for treating nulls, so it's all pretty convenient with Kotlin. So takeaway, Kotlin is good with nulls. Now the question is, what about Java? So Kotlin can call a Java API, but upon the event of the call, the compiler must somehow make up its mind. Like this Java string, is it like nullable? Is it not nullable? Yes, I. And also, if you have a list of string, it's not so few options anymore, right? It can be a non-null list of non-null string, a non-null list of a nullable string, a nullable list of non-null string, and a nullable. So we have many options, and we have to make up our mind. As type-safe people, we initially decided that, OK, we have to be on the safe side. The only option that is sound here will be say, OK, everything is nullable in Java. We don't know anything. Any reference can be null. So question marks all over the place. This kind of is sound. Of course, if you have a primitive int, it's not nullable. But everything else is. So this means that whenever I have a Java call, like to a string or something, all my dots are illegal. I cannot dereference nullable pointers without anything, any ceremony around it. So what I can do is, for example, these safe calls that do not evaluate, or basically evaluate to null if the left-hand side is null. But this picture means that all your code where you interop with Java is covered in these special symbols. And this may be a price you're willing to pay for type safety and soundness. But unfortunately, there are worse situations here. Like if I have a list in Java, and it's that list a string, right? So I think it's a nullable list of nullable strings. So the best I can do is put this double bang operator here, and it will be a non-null list of, unfortunately, nullable string, which means that it doesn't fit. So we kind of asserted that the list itself is not null, but the arguments we can do nothing about. And there is no generic way of dealing with this. So this is a deadlock for the user. There is no way of using it without an explicit cast, which would be unchecked, of course. So kind of, it's kind of a failure. The safest way doesn't actually work. I would like to have it, but it's so inconvenient nobody would put up with it. What's that? Oh, yeah. There is, of course, an option of not interoperating with Java. But that will be a very nice kind of theoretical situation. But
unsafe.
Yeah, very unsafe from the marketing or adoption standpoint, I would say. Yeah, so we tried for a while to get away with using annotations. So you can put a non-null annotation here and there, and it kind of double crosses on some of the options here. This, unfortunately, doesn't help with these, because there is Android, and it's not Java 8. There are no type annotations there. And you can, some of the libraries are not under your control, so you carry around those huge XML files with annotation information, or newer JF files with annotation information. Users forget to configure their tools properly. Annotations are lost, compilation is broken, everybody's unhappy. So, yeah?
Can you just clarify for us that Java 8 solves that problem and you are choosing not to use it?
Yeah, Java 8.
Compatibility with something else?
Yeah, thank you. So Java 8 does solve this problem of not having type annotations, of being unable to put an annotation on the string inside a list. So I can't annotate it here in Java 8, but I still am stuck with two problems. One being Android being not Java 8 and being a huge market. Another being that a library developer has not annotated his library, and I cannot possibly do it in a convenient way for my user. So again, practically, it's not working. So again, practically, you have a list of 3 requirements, and apparently you have to pick 2. We didn't want to give up on either convenience or Java, so we kind of gave up on the null safety and introduced something called flexible types with the help of Rust 8 from Cornell. OK, so what is a flexible type? A flexible type is when you collapse many options into one. I say a Java string. All I say, it's a Java string. I have no idea if it's nullable or not. I have this red exclamation mark. It's red in the code. Well, actually, it's not in the code at all. And it's a flexible type. It kind of behaves ambivalently. And when I have a generic, both of the components of the type will be generic. So the var is generic, is a flexible type or platform type, and the string inside also platform type. So what it gets us is this kind of behavior. So normally, when you have a non-null type, you can dereference it with no problem. And if you apply some null-specific operations, you get a warning because it's a pointless operation. If you're nullable, you cannot dereference, and the nullable operations are applicable. If you are flexible, you can dereference. The compiler does not complain. It may blow up. You probably remember that from the Java age, right? And the nullable operations are legitimate because they may actually make sense. So this is the flexible behavior we wanted to achieve. Now it gets a little more complicated. So before any flexibility, we had a very, very clear, nice picture when there is a nullable type, a non-null type, and one is the subtype of the other. So the one with null is wider, so you can assign a string to a nullable string with no problem. Now, you should obviously be able to assign the platform string to any of these. And of course, if you're trying to put a null, an effective null, into a non-null variable, we will emit a runtime check and blow up. But this now is not a transitive relation anymore. So normally, you would like your subtyping to be transitive. And here, it's a clear loop. You can assign, through this loop, you can assign a nullable string through a platform value to a string and blow up, probably. But from the type system design standpoint, it's an unpleasant property. Yeah.
Wouldn't it be easier to provide wrappers?
Wrappers for what?
I mean, for invoking a Java function or Java method, you provide a wrapper written in your language, checking the results and making sure that the user has a value that is different from null.
OK, so the question is, could we wrap all the Java calls we're making to have some checks there and probably annotate the wrappers correctly? In theory, yes. In practice, it violates our requirement of being smoothly interoperable. The idea is that you can throw any Java library at Kotlin with no integration work, and it will be convenient to use. So the answer is technically yes, practically no. So this picture has an unpleasant property of being circular or non-transitive. And we have to live with it. No way around. So this is, by the way, the first unsoundness we have. But it's a nice kind of unsoundness, because if you look into the gradual typing theory, and all this kind of resembles gradual typing, this is OK because it blows up here. So as soon as you violate your type system requirements, your static requirements, the runtime will blow up. It's OK. So this is the nice kind of unsoundness we are introducing into the language. So a little bit on how it's represented inside. So my types have weird shapes. So a normal string would be rectangular, The significant part is how long are the horizontal bars in the rectangle. So basically, any type may have a wide end and a narrow end. So for string, both are of equal length. And for a platform string, the wide end would be string question mark, and the narrow end is normal string. What it means is that, of course, we'll use those ends differently in different contexts. Like when I'm checking subtyping, I'm doing a funny trick of picking the most convenient end. Like if I want to check if my platform string is a subtype of normal string, so the normal string is this wide. So this is more likely to fit in. So I'm taking the narrow end and check if it's a subtype of this wide end here, like the upper end. So by the same logic, if I'm trying a nullable string, and if it is a subtype of a platform string, again, I'm taking the narrow end from here and the wide end from here. So this way, it all works. So the internal representation is that flexible type is basically a pair of bounds, a narrow bound and a wide bound. And so when we are calling methods on it, we use the narrow one. When we are working with subtyping, we use the wide one. Questions here? All right, everybody's lost. Now, next unpleasant thing here is that when we are checking subtyping on two invariant classes, ArrayList is a familiar one from the JDK. So this is invariant, which means that for this to be a subtype of this, the arguments should be exactly the same, or equivalent. And by equivalent, we can mean that A is equivalent to B if they are both subtypes of each other. With a normal type system, it means that these are same types. But our type system just has got abnormal. So what we have here, again, so string, platform string, is a subtype of nullable string and vice versa, and same here, right? So the equivalence relation is not an equivalence relation anymore. It's not transitive again. So surprisingly, all the typing rules sustain that, although it's a very unpleasant property from the mathematical standpoint. But yeah, it kind of gets unpleasant here. So all the mathematics is basically thrown away, and we have to recheck everything. All right. Yeah, and by the way, it sometimes can result in string being kind of equivalent to string question mark, and there are nasty tricks of getting rid of this. OK, so last bit is that I mentioned that we perform some runtime checks. But of course, not all of them, all of the necessary checks we can perform. Because with a simple string, it's easy. You assign to a non-null variable. You just check one value. It's OK. But now I have a list. And again, I can't check the list itself, but I can do nothing about its contents. So all I can do is say, it's fine, assign this. And there will be no check on the elements of the list, and it will probably blow up somewhere else. So this is,
Sorry, just on that first line. So the arrow is
assignability. When I'm assigning this to this.
String exclamation mark platform.
Platform type, yeah.
OK, so you're saying that if you, and it means that it might be null.
Yes.
Or it might be a
Yes.
good string. OK, and so when you're assigning it to a
Normal string, to a string that is not supposed to be null, I can make a check. Yeah. And same here. So this is a hole in the academic sense. So for a gradual typing system, this is a bad unsoundness. Because you allow something in the typed part of the language that will not immediately blow up at runtime. It will blow up sometimes, maybe. Yeah. Now, yeah, I have some notes here. So one thing is that flexible types are not part of the language. So you cannot write them down yet. We are very reluctant to introducing them, and I'll show you why in a little while. Pure Kotlin has nothing to do with them, so it's still null safe. Kotlin plus Java here is arguably as safe as Java. So you can have a null pointer exception from Java. You can have a null pointer exception from Java plus Kotlin. It's OK. Also, the annotations I mentioned before still can be used, and then we will do proper checks and turn the flexible types into inflexible ones, and then just complain about you trying to do something bad, but only if the annotations are there. And actually, the property there is that if you pull out the annotations, if the program compiled with them, it will compile without them. And it's important because people lose their annotations along the way all the time. OK, so we kind of managed the nullable. Any questions here? OK. So now I picked a nice citation from John's talk of recently. There are many APIs that talk about arrays, which will never change. And we have to deal with them. As I mentioned already, arrays in Java are covariant. We would like to make them invariant so that you cannot assign either of these to each other, because it's bad, you know. But in Kotlin, you can express something you can assign many kinds of arrays to. It is called a covariant projection. It's very much like a wildcard from Java. So you can say it's an array of out t. Out means covariant. And then an array of, this should be t or subtype of t. So an array of subtype of t will be assignable to this. This is totally broken. This is incorrect. Don't look at it. Very many typos in one line. A peculiar property of a projected type or a wildcard type is that you cannot call contravariant methods. So the compiler would not allow you to set anything into an array which is projected, obviously, because you will break it. So that's all nice and shiny in Kotlin. Now we have to enable the Java's intended usages. So we make a flexible type out of any array we see in Java. And its narrow end is the most narrow type I can give to an array, which would be an array of, so if I have a Java array of foos, it will be an array of flexible foo. And the upper bound will be the most wide type, the most permissive type I can give, which is an array of out foo question mark. Now imagine putting this into the language. Yeah, so that's pretty easy. If you check subtyping, it's that weird rule we saw. If you're trying to call a method or assign an element to an array, you're using the narrow bound. It's allowing you to do anything you can do in Java. That's all right. Again, so if you have an array of string, you check the narrow from here against the wide from here. It's all right. It assigns. So again, we're as bad as Java, or as good as Java. It's good. The next thing is collections. So we really wanted to express the read-only contract on particular references to collections. So what we did was we tried to go away from this idea of the list interface having both get and set. We wanted to split it into two so that here I can actually, without a comment, explicitly in the language say that this list is read-only, so that it doesn't fail at runtime because I return an unmodifiable list, but it complains at compile time. So list interface in Kotlin looks like this. Only has get and a bunch of other accessor methods. Then the mutable list will be a subtype of this, and it adds the mutating methods. And now if I want to return a read-only view of my collection, albeit actually mutable by implementation, I can say just list of foo is read-only. Mutable list is mutable. So at compile time, I can manage my situation. So the overall structure would be like this. These are read-only types. They don't have any harmful methods in them. Now I can extend each one of them, and I did in the library, with a mutable version. And the actual Java collections, when we look at them, the library collections, they are kind of fictitiously extending the mutable interface. So at runtime, there is still Java util list, it's all right, but at compile time, we split it into two. So in Kotlin, you can say list or mutable list, and it compiles down to the same Java util list. And we'll load the Java classes so that they extend the mutable versions.
Do you stop people casting from list down to mutable list?
The question is, do we stop people casting from a read-only list to mutable list? No, we don't. So the property is, if you're your own enemy, cast. OK. So back to flexible types. We used to have this bar loaded like this. I have a flexible bar, a flexible string, and it's all right. So as soon as bar becomes a collection, it's not only nullability I don't know about, it's also the mutability. So it's a maybe mutable list of a maybe mutable, maybe nullable list of maybe nullable string. And I have to manage it. OK, so obviously, it's, again, a platform type, a flexible type representing the platform value. And the narrow end is the most precise one. The mutable list, it's the least, the lowest class on the hierarchy I can get for it. And the wide end would be a nullable list of string. This is covariant, so this is a subtype of this. It's all right. Nothing's broken yet.
Sorry.
Yeah?
Shouldn't the lower bound also be a mutable list that itself might be null?
No, it shouldn't. So the question is, should I make my lower bound?
It's an input parameter of the function. OK.
It actually doesn't matter. So the question was, should the narrow end be nullable too? The answer is no, because if you think of string we would have not null at the bottom and nullable at the top. And this is a combination of two. We express both nullability and mutability in the same thing. So it's a non-null list here and a mutable. So the most precise I can get. And this is nullable and read-only, which is the widest I can get. And so the nice property of this pair is that I can combine two properties in the same representation.
Yeah, it sort of feels like you already need another dimension.
Well, maybe another dimension would have solved a problem I'll present in a minute. I don't know. So when we first thought about this design for collections, it seemed safe, compatible, and covariant for the read-only classes. At the same time, it looked like a rare luck when you can get something that works really for all the clients and doesn't break anything. But apparently, it's when there's no Java. When there is Java, it's more complicated because, say I have a list of objects. I represented, as I showed before, at the top I have a list of any. Any is our object. It's covariant. And at the bottom I have a list of any, a mutable list of any. Now, this is covariant again. So when I take a list of string in Kotlin, take its bottom, which is a list of string again, and check if it's a subtype of this. It is, because a read-only list is covariant, which means that I have just passed a list of string to a method that expects a list of objects, which even Java wouldn't allow you to do. And Kotlin does. So you can do this, right? I have a list of strings, and I can pass it to this foo method that can do anything. For example, put an int into it or something. That's unfortunate. And this is like the biggest unsoundness and the biggest reason why I referred to Dr. Strangelove in the beginning of it, because all the rest was kind of manageable. And this is really upsetting because this is where we got somewhat worse guarantees than Java gives you. But apparently, if you want all the things that we want, you can't get rid of it. If you want the list, the read-only list, to be covariant, if you want it to be in an interface, be implementable, so not final, and if you want to enable the interop with Java, you inevitably make it possible to make some transition from a list of string to a list of any, and then pass a list of any to Java somehow. So for example, you could do that through an extra variable, right? So I have a list of string. In Kotlin, this is a legitimate assignment. There's no problem with it while you stay in Kotlin. And through this one variable, here we still pass it to a Java method. And this is something that would be very unnatural to forbid, because it's a list of objects from the Kotlin standpoint, like if you erase it, right? And so this is totally unthinkable to forbid. And this means that we can't get around it. Any questions here?
So,
yeah.
So a bit deep here, but so the problem was that you have a list of objects, not a list of question mark.
Yes.
And you're saying a list of objects is a list of anything in your language.
A list of objects, when we see a Java list of object, we allow you to put anything into it. That's right. Yeah. A list of anything. Fortunately,
What do you do with a list of question marks then?
a list of question mark would be a little easier because it would be covariant. So you couldn't
Put anything in it, but you can take stuff out.
you can take yeah, you can take stuff out. You cannot put stuff in, but it doesn't change the picture very much. But it's safe because it's covariant on the Java side. It's not a problem. So here the problem is that we introduce covariance where Java doesn't have it. So we got rid of it with arrays, but introduced it here. So the interesting thing is that we were not aware of this problem for a while after prototyping it, for a few months at least, and nobody stepped on it. Because there are actually very few things you actually have in your APIs that are open types. Like a list of objects is very uncommon, actually. Even a list of char sequence is very uncommon. So it's not a very typical situation that you fail with this. Normally, it will blow up. I mean, it will complain at compile time. But technically, we're not even as safe as Java here. But, you know. And of course, I can always take my duct tape out of my pocket and patch a little bit here and there so that you don't do an obvious error at least. Of course, I cannot prevent you from doing something more sophisticated, but when you're explicitly passing a value typed as a list of string from Kotlin to something I know to be a Java method, I can put a check in here, like a special check. It's not in the type system. It's just a special thing for Java, and say, OK, this is forbidden. It's definitely wrong. But of course, if you do it through another variable, it will allow it anyway. So this, again, it doesn't cure anything, but it helps a lot in practice. And yeah, a little bit on runtime checks. Of course, we can check a little bit at runtime here. So we can try to make sure that nobody assigns something that is not mutable to a mutable collection. Again, technically at runtime, everything is still a collection, a Java collection. So we have to somehow put some metadata onto those. But anyway, we think that all Java things are mutable. But a Kotlin class that only extends a list and not a mutable list should not be assignable to something that is typed with a mutable list. So we have checks for that, but not if you have a collection of collections, of course. So for elements of collections, you're on your own. Questions here?
Can you do something with the bounds?
What's that?
The bound constraints in so lists of the subtype is this and the supertype is that.
Yeah, well, this all plays nicely with both type variable bounds and type inference. So this.
Does that make this solution harder, or is it just open?
Not much. Not much. Most of our algorithms were not modified in any way for this. So it's pretty transparent, which was a surprise because one would think that having no equivalence relation there or having no transitivity would be a bad thing. But apparently, all the algorithms we checked are agnostic to this. OK, few last bits. You're not supposed to eat raw, some people say. So with raw types, it's kind of annoying because it's a legacy thing anyway. So we know it was inevitable to introduce them, but we kind of think that they are not there anymore. Everybody's on Java 8. Java 4 has been very long ago. So who cares about raw types? So one thing is that people actually use raw types now and then in very many places because of this. This is just an unfortunate thing, and I wonder if it may be even fixable, I don't know. So the thing is that somebody wants to write a recursive generic. Everybody saw enum class in the JDK and wants to be as smart as the JDK people. So you introduce a T that extends the class it's a parameter for, but then you just forget to pass the T as an argument here. The problem is that the compiler does not complain in any way. And you end up with a raw type here. So as soon as you have a T anywhere, you're stuck with raw types. And this is not an imagined example. This is why we actually pay a lot of attention to raw types, because it pops out from here and there all the time. Like you load any big library, there is an example of this. So we have to deal with it. Also, there are many raw types somewhere stuck somewhere in the middle of a large hierarchy. You may not be accessing them immediately, but when we're binding overrides in the compiler, we have to see that this raw type here is actually compatible to that generic type over there. So we have to represent them. We don't do it as smoothly as everything else, but still. So when we have a row of foo, which was declared as foo of t that extends bar, we have a narrow end of just foo of bar, which is an erasure of t. Then we have a wide end of a covariant version of that, so that you can assign anything that satisfies the bound to the raw type, which is roughly Java semantics. So here, this means that if you have a Java method that takes a raw type, you can pass anything that Java would allow to it. If a Java method returns a raw type to you, it's not that smooth. It wouldn't fit into anything, only into foo of bar. So what you can do is just explicitly cast. And it's very uncommon, so we don't care. So this, again, formally, it violates our constraint of having no overhead at the call site in the code. But actually, we don't care, because it's a very rare thing. Questions here? All right, everybody's completely lost. Good.
Well, there could have been some initial reading I felt before I throw myself out into this.
OK.
Trying to keep track of the Kotlin online, too.
Yeah, so summary of the Java situation would be that with nullable types, we're more or less well off. We are as safe as Java in the sense of guarantees we give. We can throw in some annotations and be even more precise in our type checking. We can emit some runtime checks, so they don't guarantee anything, but still they help a little bit. With arrays, it's the same thing, no checks needed, same as Java basically. With collections, we are unfortunately worse than Java. We allow some covariance where it is not intended. We have a nasty patch that rules out some common cases, some common errors. We can throw in some annotations, and they help along. We can do some runtime checks again. As usual, raw types, not so important for the client, so they are usable, not as smooth as in Java, but safe enough. So, and the takeaway from here is that we're trying to put together more safety than Java and seamless interoperability. You get some kind of gradual types that are unsound in at least 2 meanings of the unsound. So you get less safety, but not so often. So it's still practical to have this. Questions here? Go ahead.
The Kotlin array types are invariant.
Invariant, right.
Why do you want that?
Again, philosophically, we wanted to get rid of the unsoundness of Java type checking with respect to array assignment. So we wanted to get rid of array store exceptions. Yeah.
Oh, wow. So it's not unsound because we checked at runtime
Yeah.
an exception
Yes.
which prevents the heap pollution that would otherwise be the result of unsoundness.
Exactly.
So since you're running on JVM that is always going to do that covariance check at runtime, I can totally understand why you wanted covariant collections.
Yes.
Every Java developer who sees a list of objects and thinks you can assign list of string and gets disappointed, wonders why they aren't covariant.
Yeah.
So I'm not going to ask about that. But the covariant arrays, what did I say the problem again?
The problem again, array store exception.
Okay.
Yeah.
It's like
So yeah, one can think about imposing safety features into the language as getting rid of runtime exceptions. As it turns out, we cannot get rid of them entirely, but we can get rid of some of them at least. More questions? OK. Yeah, so it's safe enough again. Now, yeah, if you want to play with it, just visit our website. And the last bit that I would like to advertise here is that we actually not only compile to Java, but to JavaScript as well. And JavaScript is a little less typed than Java, as you know. So there, it's even more relevant to have some flexibility, because you have no types whatever. And there, it turned out that with the same machinery, we can get something that we call dynamic type. It's not available for the JVM at the moment, because we don't know how to efficiently implement it. So a dynamic is something from bottom to top, just anything. It actually required a little bit of patching on the resolution side, because normally what we do if we're trying to resolve x.foo would be take the narrow end and ask its members. But nothing has no members, obviously. So this comes together with a few rules that allow basically anything to be called on dynamic. And this is an extra work in the language. But type system-wise, with inference and subtyping and everything there, it just works this way. So this idea of having types split into two bounds and having weird rules on those works pretty well and covers many use cases. So this would be, if you want your language to be safer than some other language but compatible, you can try to use these tricks too. Questions? All right. Thank you very much. It was fun for me, at least.